Welcome back. In the last couple of lectures, we were discussing about the Fourier transform in the higher dimension. For that purpose, we discuss very rapidly what do we mean by integration in the higher dimension and what are the differential operators, the derivatives in the higher dimension and the polynomial in higher dimension. So that leads us to define one of the most important class of functions what we have seen in our experience in one dimension is the Schwarz class function. So, let me define what we mean by the Schwarz phase. This is all f which are infinitely differentiable, and then I look at the polynomial x to the power alpha. Recall that this is if x is equal to x1 to xn, and which all these xi they belong to R, and alpha is the multi-index alpha 1 to alpha n, where alpha i's belongs to the non-negative integers, each of these alpha I. Then we have defined x alpha 1 is equal to x1 alpha 1 into xn alpha n. Similarly, d alpha of f we define to be del alpha 1 by del x1 alpha 1 to d alpha n by del x n alpha n of f, and we have denote this as summation over I from 1 to n of alpha I, mod of alpha. So, this I hit with d beta of f at x, take the modulus supremum over all x, and this is finite for all alpha beta multi-indexes. For concrete example, obviously any function which belongs to CC infinity of Rn, they belong to Schwarz place. And second part is that one of our favorite function what we have seen is that the Gaussian in dimension n equal to 1, and here this minus pi x square is going to be replaced by. So, easily one can check that this f is in Schwarz space because it has an exponential decay, and so here all these if I am taking the derivative, then e to the power minus pi x square, this is equal mod x square, this is going to be e to the power minus pi x1 square plus x2 square up to xn square, and then this is equal to e to the power minus pi xi square, and then this is the product of I from 1 to n. So, therefore, when I am applying the partial derivative to this function, then all the rest of the thing is going to come out and the partial derivative. Suppose del alpha n by del x n alpha n, which is going to be del alpha n by x n, and then the product of this by the chain rule, and then each of on each single variable the Gaussian has much more decay, faster decay than the polynomial. We simply just from our knowledge of dimension 1, we can conclude that f given by this Gaussian is in the Schwarz space. Okay, so now once we have in the Schwarz space, then we define, let f is in the Schwarz space, define f hat for xi is in Rn, xi belongs to Rn, define the Fourier transform of f at xi. So, now we need to consider, like for example, the Fourier transform for 2 pi periodic function. We have, or one periodic function, we have defined f hat of n is equal to integral 0 to 1 f of x e to the power minus 2 pi I n x, where n is an integer. For f in the Schwarz space of R, we have defined f hat of xi is equal to minus infinity to infinity f of x e to the power minus 2 pi I xi x dx. So, what we had observed that the fundamental behavior of the function e to the power I n x is nothing but it is a continuous homomorphism from the circle group to the circle group, and for R e to the power 2 pi I xi x is a continuous homomorphism from real line R to the circle group T. So, naturally here we would be interested to find the continuous homomorphism phi from R n to T. This exactly as in the case of R, we can show that, then in that case phi x is equal to e to the power 2 pi I x inner product of xi dot product. So, we will we will denote this x dot xi. So, here, so now we are all set to define the Fourier transform in higher dimension. This is f of x, then e to the power minus 2 pi I x dot xi dx. This is what is going to be our Fourier transform for the higher dimension. So, easily one can see that if mod of f hat of xi, this is less or equal to integral over R n mod of f of x, and then e to the power 2 pi I x dot xi modulus is going to be equal to 1. So, therefore, this is dx. So, f hat is a bounded as a matter of fact, in R, what we have seen is that if f is in Schwarz space, then f hat is going to be also in Schwarz space. So, that question we will address it here, and of course, this is the proof is going to be more or less same. So, let us first look at the example. Let us take f of x is equal to e to the power minus pi mod x square. Now, let us compute the Fourier transform of this f. So, now f hat of xi, this is equal to integral r n e to the power minus pi x 1 square into e to the power minus pi x 2 square e to the power minus pi x n square, and then e to the power minus 2 pi I x 1 xi 1 e to the power minus 2 pi I x 2 xi 2 and e to the power minus 2 pi I x n xi n, that is the dot product, and then this is dx 1, dx 2 and dx n. This is the Riemann integration, and here this R n integral is, this is R, this is n copies of R, then this. Now, if we like, if we will do the repeated integral by pulling out the other variable and only we perform one integral, then this is going to be, let us say, we will write it down for 1, this is R, this is n minus of 1 copies e to the power minus pi x 1 square multiplied by e to the power minus pi x n minus of 1 square, and then e to the power minus 2 pi I x 1 xi 1 x n minus 1 xi n minus 1, then the integral e to the power minus 2 pi x n square e to the power minus 2 pi I x n xi n dx n, and then this dx 1 to dx n minus of 1. So, this is nothing but what we know, that this is e to the power minus xi n square. So, similarly, if we perform each integral, then this is going to be e to the power minus pi xi 1 square, e to the power minus pi xi 2 square, e to the power minus pi xi n square, which is equal to e to the power minus pi mod xi square. So, the Fourier transform of the Gaussian is again a Gaussian. Okay. There are several important properties of Fourier transform what we have observed for R, that how the Fourier transform behaves with translation, dilation, and in R we do not, we have the reflection where that is x going to minus of x, and here the reflection will be replaced by a rotation, that is means x will come to that. First the translation, we define that let a y belongs to Rn. Then we define tau y of f at x. This is equal to f of x minus of y. So, therefore, when we have defined this is so tau y f hat at xi, this again just using the r, we have f of x minus of y e to the power minus 2 pi I x dot xi of dx. Now, if I make a change of variable here, then this is f of x e to the power minus 2 pi I x plus y, then this is xi dx. By making a change of variable x going to x plus y, and then this is nothing but Rn integral over f of x e to the power minus 2 pi I x dot xi into e to the power minus 2 pi I y dot xi dx. Now, this is independent of x. So, as earlier we get it heated, the Fourier transform gets heated with the character e to the power minus 2 pi I y xi x. Then modulation define that means m of y of f of x, we will define e to the power 2 pi I y dot x f of x. Then m y f hat at xi, this is going to be again Rn e to the power 2 pi I y dot x f of x e to the power minus 2 pi I x dot xi dx. Now, this is equal to, in Rn we know that y dot x is equal to x dot y. Therefore, what we can get is this is f of x e to the power minus 2 pi I, and this is x dot minus, if I am taking xi minus of y dx. So, this is nothing but f hat of xi minus of y. So, if we are taking the translation then taking the Fourier transform, then we get heated by character, that in fact the modulation of f hat. Now, if we take the modulation and we take the Fourier transform, then the Fourier transform gets translated. And then the other important thing is that dilation. So, let delta greater than 0 define d delta f of x, this is equal to 1 over delta to the power n. In the case of r, we have defined just 1 over delta, and then this is x over delta. So, now exactly as in the case of r, if we compute the Fourier transform, then this is Rn 1 over delta to the power n f of x by delta e to the power minus 2 pi I x dot xi of dx. Now, we will make a change of variable, let us say y equal to x by delta, then dy which is equal to dy1 dy2 to dyn. So, on each factor I am going to, this is essentially x1 by delta up to xn by delta. So, this is 1 over delta to the power n dx. Just simply now if we put this, then what we can get is that this is f hat of x, this x becomes x into delta. So, therefore, this is delta of xi. This follows exactly the same argument as in the case of R. Then we have something in Rn in higher dimension which we do not have in one dimension, that is called rotation. So, we can define a rotation R f at x which is equal to f of a x, where A is an orthogonal matrix. So, which means A star is identity. If I have a vector in Rn, then if I apply a orthogonal matrix, then it is going to rotate it to another vector. So, this is now we say then what is going to happen with R f hat at xi. Now, this is going to be R n f of a x, and then this is e to the power minus 2 pi I x dot xi dx. Now, if I am going to make a change of variable, suppose a x we are writing at y, then x we have a star of y, because a star is the inverse of a. So, therefore, the x dot xi, this becomes a star y dot xi, which is nothing but by the matrix operation. This you can symbolically can think of this dot product is nothing but the inner product. So, this is xi. So, if you take to the other side, then this is going to be a xi. And then when I take the, then the dx, this change of variable will say that the Jacobian is going to appear, and in this case what we know that the determinant of A, this is equal to plus or minus 1. Therefore, modulus of the determinant is going to be 1. So, hence by making a change of variable we get that f of x e to the power minus 2 pi I x dot a xi, and then this is dx, which is equal to f hat of a xi. So, this calculation easily so that if, so now what we will define a function f is said to be radial if f of x is equal to f of y, if wherever it is mod x equals to mod y. That means, this function is going to be determined if I have, this is x, any wherever it is lying over here. So, x is lying here or here, whatever, or here in this matter. So, f is going to take the value, the same value on this sphere, which is the mod x, the sphere of radius mod x and centered at 0. Now, from this previous calculation, one can easily see, what one can see is that if f is radial, then f hat is also radial. So, that means what, suppose if I am looking at this any x in this sphere, then I am saying that on this sphere f is taking the constant value and f hat will also take the constant value. That means, from any point here, suppose if I want to compute f hat at this point, then I can find a rotation a such that x I can transport it to this point on the sphere. So, here that is what our RF now has become. So, this what we know is that it is essentially f hat of Aj. So, therefore, it is going to be the constant all throughout on the sphere of the radius x. So, that is one very important property which we would like to exploit in our journey into the higher dimension Fourier transform. Okay. So, now while dealing with R, we saw that the behavior of the Fourier transform under the derivative and the Fourier transform of the function which are heated with the polynomial, they play a very important role in R. And here in exactly in the same fashion, if we want to check that if f is in Schwarz space and we would expect f hat to be in the Schwarz space, that means what we need to check is that all the derivative of f hat, they have very good decay, they decay rapidly, and then we can have a control for every fixed multi indices alpha and beta. That is what I mean to say is that what we need to look at d alpha of f hat and then of xi, and then this is xi to the power beta some multi index, and then we would like to take the supremum over xi. This is what we would like to control, and if we can manage to control that, then f hat is going to be in the Schwarz space. So, in the next lecture, this is what we are going to see, that we can control this, and the proof is just a bookkeeping as that is in R. Nevertheless, we will write down the sketch of the argument that how to conclude if f is in the Schwarz space, then f hat is also going to be in the Schwarz space. Thank you.